In the last video, we had a discussion on the type of crystalline solids. There we have seen BCC, FCC and simple cubic structures. With the help of the diagram we have seen. Now, today we are going to go into the mathematical portion of this chapter. Here we are going to discuss these topics: type of cubic crystals, number of atoms in a unit cell. Unit cell already we have mentioned. Today we are going to see the number of atoms in each type of unit cell and the packing efficiency. So to understand this, I will like to request you to see this video in the highest bit possible video quality so that you can see the diagrams carefully. There are some mathematical portions associated with it that also we have to see very carefully. To understand number of atoms in a unit cell, let us take a simple cubic unit cell as I have drawn. We know that at every corner there are atoms. So 1, 2, 3, 4, 5, 6, 7, 8. If this one is the main cubic unit cell that we are talking about, then in this 1, 2, 3, 4, 5, 6, 7, 8, in all these 8 corners, this red atom, red ball or red atom, spherical it is, we are assuming itself to be spherical, should be there. Now the point is, in that logic, going by that logic, there should be 8 atoms per unit cell in a simple cubic unit cell. Whether actually it is the case, let us see. So to understand that, let us assume this one as a cube. Suppose one atom is here. So see, if a ball is here or an atom is here which is spherical, the full portion of it will not be within this part. The part of my hand will be outside of this box, of this cube. What does it mean? A substantial amount of the part of this atom is out of the actual unit cell. So let us see that with the help of a video, that actually how much part of this atom or the ball is within this cubical unit cell. Let us see this. In order to check the closed pack structure and in order to understand the contribution of individual atom within the unit cell, check here. So if they are closely packed, they will come very close to each other. Now see the proportion of it within the unit cell. See, one atom is basically being shared by 8 unit cells. So 1/8 of its volume is actually within an unit cell for corner atoms. So we have seen that how much space of the atom or how much volume of the cornered atom will be inside the cubic unit cell. So if you can remember, for any body centered atom, roughly how it is going to look like, just to recall. So in the last day's video, we have seen that the atoms will be here, means in all the corners. So for corner atoms, the situation already we have seen, and there will be one extra atom here inside, this one, and this one was called the body centered. Same thing I have drawn here. So the topic should be for body centered atom. So here it is. So if you see it carefully, for body centered atom, if you see this cube once again, the position of the body center will not be in any of its face. It will be fully within. Means it should be fully within the cube. So it is fully within. Any part of this particular atom is not outside of the unit cell. So the contribution of the volume of this one will not be less than 100%. It is fully inside. So how many body-centered atom is within the unit cell? It is number of atom, means obviously for body-centered will be 1 into 1, that is 1. Again, this is fully inside, so total part of this atom is within the unit cell itself because it is exactly present at the center of the body. So it is 1 into 1. But here, if we are looking at face centered atom, first of all, where the face centered is located, you see here. Suppose this is a cube. So here 1, 2, 3, 4, 5, 6 faces. And center of the face means, suppose this is a face, here in this region at the center of the face this atom will be present. So that is a face centered atom. Remember, one atom, if it is present here, there will be another cube here. So that ball or that atom will be divided into this cell as well as the other cell, which I could not show right now. If an atom is here, half part of it will be outside, half part of it will be inside this box or inside this cube. So imagine there are another cube here, so the ball will be fully inside or the atom will be fully inside. That means it is divided by 2. That is what has been drawn here. You see this red atom, obviously half part of it will be on this side. That means this blue unit cell, and the rest of the part will be towards the right hand side, which is the black unit cell. Half part of it will be on this side. So it is going to be divided here. Half part is here, here also half part. So the contribution for face centered atom, so for FCC atom, or rather for face centered atom, the contribution is half into 1. That means for one atom, half of its portion will be within a particular unit cell. So now let us calculate the actual number of atoms per unit cell. So already we have understood that in a cubic unit cell or in a BCC or in a FCC, there are different type of atoms like corner atoms, FCC atoms, face centered atoms, body centered atoms. What will be their contribution in a particular unit cell? Now suppose for simple cubic unit cell, it will look like this. Here there are corner atoms only. But there are atoms present only at the corners. We know it already. And in the 3D diagram, in that video, you have seen that their contribution is 1 by 8. So let us draw BCC and FCC also, then we will write it together. For BCC structure, it should be like FCC also. So I've drawn the cubes only. Now fill up the atoms. Let us fill up the atoms. So for BCC, the corner atoms will be there as usual as for simple cubes, 8 atoms. And we know here also, let us fill it up together. So we have drawn the corner atoms, 8 atoms in all the cases. In simple cube, we know that these are only the atoms that is present, but in case of BCC, we know at the body center there is another atom. This is the body center atom. And in case of FCC, at the center of each faces, 1, 2, 3, 4, these 4, and 1 towards us, that is here, and 1 behind of it, that is here. So there are 6 atoms. We have drawn it already. I hope this one better, I could draw it here. Center of this face. So there are in total 6 face atoms, face centered atoms. Now let us calculate. We know for corner atoms, the contribution, it is the contribution into number of atoms. Contribution for each corner atom, we have seen already, it is 1 by 8. And how many atoms are there? 8 atoms. So the total is 1. That means effectively it is the volume of one atom is actually within the unit cell. Let me specify it once again. There are total number of 8 atoms, 1, 2, 3, 4, 5, 6, 7, 8. But for individual atom, it contributes only 1/8 of its volume. And since there are 8 number of atoms, so the total number becomes 1 by 8 into 8, which is 1. There are no other atoms. So for simple cubic, it is the volume of one atom which is actually within, although there are 8 atoms. In case of BCC, there are 2 types of atoms. One is corner atoms and one is body centered. So for corner atoms, same logic, each contributes 1 by 8, 1 by 8, and there are 8 atoms together, so the contribution is 1. And body center, we know how much it contributes totally its volume, that is 1, because it is fully within the cube. So it is 1 into 1. 1 is the contribution and 1 is the number of atoms, so it is 1. So in total, it is 1 plus 1 is equal to 2. So if the question comes in the body centered atoms, how many atoms are effectively within the unit cell? Answer should be 2. In case of face center, so there are corner atoms and then there are face centered atoms. For corner atoms, same rule. 1 by 8 into 8 gives rise to 1 because there are 8 corner atoms. Now for face centered atoms, we know that each face centered atom, we have seen it already. How much does it contribute? Half. So it contributes half. How many? 1, 2, 3, 4, 5, 6 into 6. So it is 3. Means 6 atoms are there. Each contributes half. So the total contribution becomes 3. So the total amount becomes 1 plus 3 is equal to 4. So in body, if face centered atoms, there are 4 atoms effectively within. in body-centered atoms there are 2 atoms effectively within, and in simple cube there are 1 atoms effectively within the unit cell. And this calculation will be vital in the, this concept will be vital in the next whatever calculation that we do. So here we can see the contribution of the atoms within the body face centered is maximum because there are 4 atoms present. Up next, we are going to see the relationship between the radius, which is small r, of the atom. We are assuming atom to be spherical, so that's why radius has been assigned as small r, and the edge, which is A, of an unit cell. So let us understand what are these first of all. Forget about the black lines. Imagine only the blue lines. That means this basic unit cell. Edge. So there are 1, 2, 3. These are the edges on this cell. Means for a unit cell, these are the edges. And if it is cube, all of them should be same. Although it's not a cube, exact cube, but actually it should have been same. So these are the edges. So edges have been considered as A. So this is A. Similarly, this is also supposed to be A. The point is radius. You see, this is actually a spherical one. You must have understood. I am not drawing it because this is actually a sphere. 1/8 of its portion is actually within the unit cell. So this part of the sphere is within the unit cell. So we are considering this much to be r. So this is also r. Radius. Here also it is radius. Now why we are drawing like this? The difference between, if I draw it very quickly, you must be thinking that earlier I have drawn something like this. Suddenly I have drawn this. The reason is this is a closed packed structure. We are trying to imagine that the atoms are very close to each other. Between them there is hardly any space or the minimum space. They are closely packed. Like in a suitcase, you are packing your luggages as closely as possible. So we are considering the closed packed structure as of now. And in that case, what should be the scenario? That is what only we are observing. So we are considering the atoms to be very close to each other, like this. Okay. Now, suppose this is A, this is B, this is C, this is D, like that. So obviously, it is equal to AB, which is the edge, and AB is also equal to 2R, because see the radius 2R will combine to give A in case of simple cubic. Remember, in case of body centered, this structure will be different, that we will see. So AB is equal to 2R, which is equal to A. So we can say that is A is equal to 2R, or R is equal to A by 2. These two, this relation will be very handy. After understanding the relationship between A and R, in case of simple cubic, remember, because in case of BCC and FCC it is going to change, we will calculate here packing efficiency. Now what is that? Packing efficiency means how much the atom contributes, the volume of atom contributes within the unit cell, whether it is more or less, that we can calculate. How better it is packed, how closely it is packed. So for that we calculate volume of all atoms present within unit cell divided by total volume of unit cell. That means if in an unit cell there are, say for an example, 3 atoms or 4 atoms, in case of a simple cube it is only 1 atom, in case of BCC 2 atoms, and in case of FCC there are 4 atoms, what will be the total volume of that 4 atom? That will be here, divided by the total volume of the unit cell into 100%. Now, you see here, how many atoms are here? In case of simple cube, we know 1. And if it is supposed to be spherical, it should be 4 by 3 pi r cube. There are only 1 atom, right? Divided by the volume of unit cell. The volume of unit cell, if the age is A, age length is A. So the volume of unit cell should be A cube, of course, into 100%. Now R is equal to A by 2. So 1 into 4 by 3 pi, R means A by 2 whole cube divided by A cube into 100%. You can further calculate it here. It should have been 4 pi A cube divided by, here you see 3 will come, A cube will come, that is 8 also, that will come into 100%. That means this will cancel out, so it is pi by 6 into 100%. On calculation, you will get it almost equal to 52.4%. So this is the packing efficiency for simple cubic unit cell. This suggests how efficiently it is packed. It is 52.4%. Later on in this chapter, we are going to calculate after this the same for BCC as well as FCC.